We're very happy to introduce today's speaker, Martín Szyld from Dalhousie University, who will be speaking to us about fibrations, filtrations, and fractions, or the 3 Fs for bicategories. We'd like to encourage everyone to make questions at any time during or after the talk. Questions can also be asked in Spanish. And in that case, Martín can answer the questions in Spanish, of course. Yeah, please, Martín, take it away. Thank you very much.
Thanks a lot. I'll then start sharing my screen. Great. So if anyone has any kind of problem seeing the content, please feel free to interrupt. Also, if you can't hear me all right. And if you don't understand some of the words that I'm saying, you can also interrupt in English or in Spanish, whatever works. All right, so thank you all for being here. Thank you very much, Juan, and to the seminar organizers for this chance of speaking here and present our work. I should say that the results I will present are part of a collaboration with Pablo Bustillo from the École Normale Supérieure in France, and with Dorette Pronk here at Dalhousie in Canada. So maybe just to give you a bit of background, we started our research looking at some properties of localization by fractions. And we were kind of led to look at the homes of the localization by fractions. And these are filtered colimits. So in general, in dimension 1, they are filtered colimits of sets. And in our case, they are filtered pseudo-colimits of categories, but it's kind of the same idea. And that's kind of what we wanted to rescue, okay? So if this makes any sense to you, then that's great. If I'm saying words that I have not defined and are weird, then you can just ignore it because I won't really focus on that for the talk, but it's just like the background. And so we started looking at how to compute these filtered colimits, and this is what led us to the SGA result that I wanna start the talk by looking at. So this is an old result, like 50 years ago. And the idea, before I get into the details, is that you have a fibration. So you have 2 categories, one on top, one on the bottom. And if you want to compute a colimit, what you will end up doing usually is to localize the category on the top at the Cartesian arrows. So it is convenient, as you may be aware, to localize using fractions, because that gives better localization. But for that to be true, you need some axioms. You need some properties of the family of arrows that you want to localize at. So the idea of the result is that if you give some properties, of the category on the bottom, then you can lift those properties to the Cartesian arrows on top and use that to localize by fractions, okay? So that's always the idea to have in mind, even though we will actually be looking just at the result here with the fibration and everything. So I won't really care about the localization, but we will be focusing on this result. And the main application is that you want to compute the localization on the top by fractions in order to compute a colimit of categories, of bicategories, something like that. All right, so let me start by reviewing then this result. So this is a result which is just for categories and functors and fibrations, things like that, okay? And it says that if you have some axioms on the bottom, which I'm writing like for each and exist, so red means for each. So if you have 2 arrows like that, then you can make them equal there. And if you have 3 arrows satisfying that the 2 possible compositions are equal, then you can find a new blue arrow, which makes these 2 compositions equal as well, okay? And the result in the SGA says that, those axioms in B imply the fractions axioms for the Cartesian arrows in E, okay? So I will not start, but I will recall some of these notions, just for us all to be on the same page. And they make the note that these axioms are implied when the category here in the bottom is co-filtered. Okay, so that's in a sense why we want to compute filtered colimits, or that's filtered colimits, because we want to consider the opposite category here by applying this to the case in which B is co-filtered. Okay, right. So that's the result to keep in mind right now. Okay, right. So let's give some background, some terminology of what I mean by some of these words that I have not defined. Okay. So maybe we should start with here the axioms for a category to be filtered or co-filtered. So co just means that you're doing the dual. So if you're filtered, then you can always go in this direction, like from the right, say, to the right. And if you're co-filtered, you can always go to the left. Okay. And the only reason why I'm introducing here co-filtered is because that's the one that we'll use. But usually you define filtered, and you say that co-filtered is just the dual notion. Okay. So let's not read the statement in yellow yet, and then we read that a category is co-filtered when every finite diagram has a cone. Okay, so that's a cone, like in the definition of limit, as simple as that, as natural as that. So in these examples here, so let me continue reading maybe. So some particular finite diagrams are enough, and these diagrams give the axioms. Okay. So you have some axioms, which I wrote here as cofield 1 and cofield 2, which are part of the definition of being co-filtered. Okay, and they are the same, they are equivalent. You can show that. It's an easy exercise to show that they are the same to asking that any finite diagram has a cone. Okay, and again, I'm using the red and blue. So what I mean here is that for each pair of points, you have a new point and 2 arrows on the left. And in co-filtered 2, I'm asking that for any pair of parallel arrows, you have a new arrow, which makes them equal, which equalize them. Okay, I should say, yeah, probably co-equalize them. You get the idea. All right. And the way I want to think about pseudo co-filtered is exactly the same as filter or as co-filtered, except that you only want to say that the connected diagrams have cones. Okay, so you don't want every finite diagram to have a cone. You just want the connected ones. Okay, and by connected I mean simply that even any pair of points you can give a finite sequence of arrows going in both directions from one to the other. Okay, so connected in that sense. And the only difference, if you want to look at pseudo co-filtered instead of co-filtered, is that so the axiom number 2 remains the same, because if you notice, in axiom number 2, the part in red is already connected. But in axiom number 1, the part in red isn't connected. Okay, and that's why you want to change that axiom. And you change it in the easiest way to connecting those 2 points with the span of length 2. Okay, so you have a new axiom, which is the first axiom for pseudo co-filtered, which asks for this, if you have these 2 arrows in red, then you have these 2 arrows in blue, making here the diagram commute. Okay, great. So that's just background on what it means for a category to be co-filtered. All right. So as you may guess, the plan is to look at everything first in dimension 1, and then see how you can kind of naturally generalize that to dimension 2, that is to 2 categories or 2 bicategories. Okay, and if I don't have enough time, then at least we will all know something more about dimension 1, which I think is always a takeaway, at least. All right, so let's recall the theory of vibrations, mainly to present them in a way that allowed for them to be generalized to bicategories. So this is work by Buckley from 2013. So first, the usual vibrations, the one-dimensional ones, the ones that go back to Grothendieck. What do you ask for a functor between categories to be a vibration? So again, using red and blue, you ask for each arrow in the bottom, if you fix here a point on top, which is, so I usually draw, well, not just me, you usually draw diagrams like this when you draw vibrations. So when you draw a point on top of another one, you mean that the functor P maps the red point here to the red point there, and likewise the arrow to the arrow and the point to the point. Okay, so for each situation which I drew in red, there exists a Cartesian arrow lifting the red arrow in the bottom. Okay, and what does it mean for an arrow to be Cartesian? So you can give a diagrammatic definition. Sorry, again, I keep tapping my pen, and that's what does that. So you can give here a diagrammatic definition, which is maybe the most usual one, the one you start with. And so again, that means that if you have U, so this is in the bottom, so this is in B, and this is in E. So if you have U and she like that, and the U makes the diagram, no, sorry, just U and she like that. And I'm saying what it means for F to be Cartesian. So it means that, yes, sorry. And it means that if the diagram here in the bottom commutes, so here you have P of she and here you have P of F, which I'm not writing because they come from she and F. If the diagram in the bottom commutes, then there is a unique V on top of U, making the diagram on top commute. So that's just the definition of the Cartesian arrow. But what I want to point out, which is already quite well known, but I still want to recall it here, is that this property can be expressed by saying that H here is a bisection of sets. Okay, so anytime when you do some kind of higher category theory, you're always interested in finding the definition that in dimension one that generalizes in the most natural way or in the easiest way to higher dimension. Okay, and this is the one that does that can be generalized to bicategories or even to more general situations. Okay, so just to give you the idea of why this is so, saying that this arrow here is a bisection of sets is saying that since H is the arrow induced by post-composition with F and applying P, so this means precisely that given something here in red, so I'm using red here because here we have the pairs U, she. So saying that this is a bisection of sets means that it is surjective. So this is what says that there are liftings like that, because for any U and she, then you have a B here. That's what means that this function is surjective. But I also want to focus, because that's the property that we will be using soon, on that it is injective. Okay, so what does it mean for it to be injective? So this is kind of a property of Cartesian arrows. And I'm writing it here as cart for Cartesian 1. So for it to be injective means that if you have V and W here, then if they are equal here and they are equal here, then they are equal. Okay, so if they are equal after composing with a Cartesian arrow and they are equal after applying P, then they are equal. Okay, so that's a property of Cartesian arrows that we will be using shortly. So try and remember that, at least in those terms, that if you compose with F and you compose with P and they are equal, then they are equal. All right, wonderful. So before I do a third reminder of a theory, let me remind you that you can interrupt if needed for any kind of clarification. All right. So finally, let me remind you of the localization by fractions in dimension 1, as in Gabriel Szyldman. So I'm thinking here of fractions as a set of axioms on a pair given by a category and a family of arrows. So, and I'm thinking of those axioms as some properties that make the localization at W easier to construct, or more manageable, or smaller in size. It has better properties. Okay, so let's just kind of naively think of these axioms in that way. Okay, and you have a list of those axioms that I'm denoting here by frac 1, which I don't really care too much about now, but you require W to be closed by composition and to contain the identities. And you have 2 kind of more diagrammatic axioms, which are much more similar to the ones of pseudo-cofilter. Okay, so here I'm using a little circle to mean that an arrow is in W. Okay, so that's why I'm writing circles here, because it works in general. W can be the Cartesian arrows, or can be any arbitrary family. Okay, so instead of using a C, I'm using a circle. Okay, and the axioms, like I said, are quite similar to the ones for pseudo-cofilter, except that here you ask one of the arrows to be in W, and you require the opposite one to be in W as well. And here you require, sorry, you are kind of a bit weaker, because here you have 2 arrows, but not any 2 arrows. You have 2 arrows which are co-equalized by an arrow in W, and then you require, I don't care about that, you require an arrow in W to equalize them. Okay, so if you have these 3 arrows in red and H is in W, then you can ask for K equalizing F and G to be in W as well. All right, so what do I want to do now, depending on how much time I have? I think I want to quickly review the universal property of the localization. Okay, writing it like this. So what does it mean to localize at a family of arrows? It means to make that family of arrows into isomorphisms. That's what iso here stands for, into invertible arrows in a universal way. Okay, and you can express that by saying that you have a functor here mapping the arrows in W to isos, which is universal in the sense that any other will factor uniquely through that. And that same universal property can be expressed by this isomorphism of or equivalence of categories, depending on your taste. Okay, so if you write here a small w to denote precisely the functors mapping W to isos, then what this says here is that it's the same to have something from C to D mapping W to isos than to have something from C W-1 into D. Okay, so if you just make the variable here mute, then you see how this this statement is just the universal property of the localization by fractions. Okay, so maybe I'm asking you to remember too much, but try and remember this too, if possible. All right, so with all this in mind, let's go back to this exercise and see if we can make more sense out of it. And sorry, so I said exercise because this is a proposition in the SGA, but the proof is left to the reader. And like I said in the abstract, I want to kind of show you how you can solve this exercise because that's what we did in a sense, and that's where the new results come from. Okay, so I kind of went over that too quickly, but let me, so remember that you have B here, and you have some axioms in B, okay? And for example, now we will assume that B is pseudo-cofiltered, like I just recalled, and I will show how asking for B to be pseudo-cofiltered implies the fraction axioms for the Cartesian arrows on top. Okay, so that's the plan. That's what I wanna do now. Okay, so like I said, I won't really care too much about the first condition for the Cartesian arrows. It is kind of well known that the Cartesian arrows satisfy these two properties. Okay, but I do want to focus on how the Cartesian arrows satisfy the diagrammatic fractions. Okay, so I want to show first how you show that if you have one of the axioms for pseudo-cofilter in B, then you get one of the axioms for fractions for the Cartesian arrows on top. Okay, so let's see how you can prove that. So to prove fractions on top, you will start with something like this. Okay, sorry. So before I get started, because we have a strategy here, which will apply to all the axioms, and I'd rather recall that now because I'm using 3 colors for the 3 parts of the strategy. Okay, so we have this fibration, and so first we will apply P, this functor P, and we will use the axiom below. Then we will lift to Cartesian arrows, using that we have a fibration. And finally, we will use some properties of Cartesian arrows. And I chose red, green, and yellow for doing that. Okay. So we start with the ones that I marked here. I'm marking now in red. And we apply P, so we are here in the bottom. We apply the axiom, so we apply the pseudo-cofiltered axiom in B. And so we get the ones in red. And then we lift each of the red ones to Cartesian arrows. That's what's marked here in green. And finally, we use, and that's the yellow here, we use one of the properties of the Cartesian arrows. More precisely, the one that gives you the liftings. Okay, you remember how I drew 2 triangles, one on top of the other? So this is exactly the same situation here. You have a diagram which commutes in the bottom, and you can lift that to a commuting diagram on top. So it really is as simple as that. So I agree that this can be an exercise, but I still wanted to do it. So here I'm just writing the axiom that you get. Okay, so again, red means for everyone, for every, and blue means what you get. So you start here with the red ones, which I drew in black here, and you get the ones in blue, which are the ones here. Okay, great. So now we want to kind of play the same game with the other axioms. Okay, now is maybe where things got a bit more interesting in a sense. So we kind of know what we need. We need the other axiom for fractions in E, the one that said that if you have F, G, and H, where H is Cartesian, then you can get K Cartesian equalizing F and G. And so you start here on the top, on E, with so we don't have that one yet. So we start here with this part. Again, we apply P. Okay, and now we use the second cofiltered axiom. So I don't know if you remember, the second cofiltered axiom was the same as the one for filtered. So the axiom for filtered only required this part of the diagram to exist, and just by that you had the red arrow. Okay, so this may seem like a small point, but this is really the big point. And I'll go back to the proof in a sec. But if you look at the result in the SGA, then they are careful. They are more careful than what I was being here in the talk, and they write here exactly this axiom, the one that has the arrow here on the right. Okay, and then they say that the axioms are implied by B being cofiltered, but they don't really say that the result is just that if you are cofiltered, then you have fractions on top. Okay, so going back here, let's just for the moment ignore that issue and continue the proof. And so what do you have? You have P of F and you have P of G, and then just by the axiom of cofiltered, without even using P of H, you can get here your K, which satisfies this equation. And again, you can lift K to a Cartesian arrow, K hat. So remember, you can always lift two Cartesian arrows, fixing here the codomain, that one here. And now you just want to show that you can choose the K here to be K hat. Okay, and so what you have to show is that K hat. Let's write it like that here. So what you wanna show is that F precomposed with K hat is the same as G precomposed with K hat. Okay, and now is the moment to use precisely the property of Cartesian arrows that I recalled, the one that came from H being injective, because both these arrows, both Fk hat and Gk hat, satisfy that if you post-compose with H, which is Cartesian, they are equal, and if you apply P, then they are equal too. That's by construction, because they satisfy here this equation. Okay, so since they both satisfy these two things, then what the Cartesian one property said is precisely that they are equal. Okay, so that's how you solve the exercise in the SGA. Okay, well, at least that's maybe the shortest way in which you solve that exercise, and yeah, and you arrive to that after doing. If you're like me, at least you arrive to that after doing less smart ways. Okay, so first you do some less smart computations, and then you realize what was really going on, and that's why I think it really makes a good exercise. Okay, so I'm sorry I kind of did that for you, but well, I had my reasons. That's kind of what I want to emphasize. I had my reasons for doing this exercise. All right, so let's look at how this situation would be like in dimension 2. Okay, so when we think dimension 2, personally I think 2 categories, because I like my things to be strict, but at the same time, the same computations always work for bicategories, where everything is pseudo, and some things can even be lax. And of course, that's how you eventually write the results. But when you think, at least if you don't want to be overwhelmed with coherence, you think 2 categories. Okay, all right. Even with that being said, as you see, I wrote by here, but feel free to think strictly. I know I will. So how do you define what it means for a 2 category to be cofiltered? Okay, so just in case, when I'm thinking 2 category, I'm thinking that not only do I have objects and arrows, but also I have 2 cells between the arrows, and I write this symbol to mean that you have 2 arrows and a true cell going in one direction, which is invertible in the sense that you can compose with an inverse in like that or like that, and it gives identities. Okay, so that's pretty much all we really need to know about two categories here. So, and the basic idea that you kind of want to replace equality of arrows by existence of an invertible two cell. Okay, so let's just keep those very basic ideas in mind and see where they lead us. Okay, so we don't really want to touch this axiom here because there are no two cells. Here we want to put an invertible two cell between compositions, and here two. And then you realize that that's not really enough, because when you're in a category, you only had arrows, you only had, objects and arrows, and you ask to equalize those. But if you're working in two categories, then you also have two cells, and you want to be able to equalize those as well. Okay, so I'm not really presenting anything new here. This goes back to a Kennison paper in the 92, I think, maybe the 96, but I'm happy to send you any reference you want. I didn't want to really write them here because it was a bit too long, too much. So there is a third axiom to add if you want to do a cofiltered two category, which is simply that if you, I'll finish this and I'll go to the question. So that if you have two parallel two cells like that, then you can have an H such that you can do alpha H and it will be the same as beta H, because you can always compose two cells with arrows and you can ask for those compositions to be equal. Okay. So that's not something, that's a good question. So I'm getting a question here that says, the result was proved only for co-filtered, let me say co-filtered categories, and if that's enough to prove the result. So maybe I should go back here and say that you're making a good point, because I was focusing on what happens if you want to show that co-filtered implies the axioms. But like I made the comment, the actual result that you want to use is a tiny bit weaker, which is the one here in the SGA, which is the same number one axiom, but a different number two axiom. And if you do that, then you will get a very slightly different proof, but that will be the correct one. Okay. So in a sense, what I showed here is that cofiltered 2 implies fraction 3. Okay. But with the same proof, you could show that the one in the SGA also implies frac 3. Okay. So I kind of wanted to leave that for in 10 minutes, where I will revisit this looking at fractions, but no, not at all. It's not something that you pass, but you're asking, does make sense? So I proved the result for cofiltered, and that's not entirely enough to prove exactly the result in SGA. It's enough for all the applications of the result where you really want to compute filtered colimits. Okay, but it's easy to be mixed, to be confused, and that's kind of what happened to me. So when I present results, I present them from the three of us. When I present mistakes, I will present them as my own. So in a first attempt and in a first confusion, I attempted the proof by using pseudo-cofilter. Okay, but if you attempt the proof with this, then the same proof works. Okay, and it tells you something which is even stronger, which is kind of the result that I want to present, which is that fibrations lift fractions. Okay, but don't let me get too much carried away. Let me try and go back to actually introducing all the notions that we will need. Right. So let's just remember that if you want to do co-filter two categories, then in addition to putting invertible two cells, you also need one extra axiom, which requires that you can equalize parallel two cells. No problem at all. Thank you for your question. All right, so that's for co-filtered in dimension 2. Fibrations in dimension 2. So we have fibrations of bicategories, which are basically introduced in two papers, one by Hermida in the 99, one by Buckley in 2013. And I wanna present them as saying that you have this same situation. So here you have, say, a two-functor, pseudo-functor between bicategories. Right, so let me go to this question. So are there any coherence requirements for the two isos realizing the co-filtered axioms in dimension 2? So the answer, if I present them like this, then my answer is no, because you don't really need those. So here you just ask for 2 points and arrows, and here you're just asking for one iso, so you don't really have coherence, even if you're as weak as in a bicategory, because you're only doing one composition, so you're not really worried about associativity or unital or anything like that. And here you just ask for equality of two cells, because you don't have any higher structure. So when you don't have any structure above 2, you ask for equality, because there's nothing else you can do. Now, no worries. I will use your question to say something that I forgot to say, which is that I presented the filtered axioms just as a new axiom, but you can also introduce co-filtered by saying that a two category is co-filtered. Let's just say co-filtered. You can even say two co-filtered or bi-co-filtered when every finite diagram has a pseudocone. Now you see why it's really bad to use always the same words in category theory. So here you have the word pseudo, and here you have a word pseudo, which should be taken with a completely different meaning, right? Here pseudo just means that you wanna use connected, and here pseudo means the usual notion of pseudocone, in which you put invertible two cells instead of asking the triangles to commute. Okay, so keep that in mind. But so a two categories two filter precisely when every finite diagram has a pseudocone, in the sense of two limits and two category theories, and two category theory and pseudo limits. So if you present them like that, then there is some coherence going on, okay? Because there is some coherence in the axioms for a pseudocone, okay? If you present them just like that by 3 axioms, then you don't really worry here about coherence, because your diagrams are too small. All right, so thank you, Juan, for your question. And so let's go back to fibrations in dimension 2. So I was saying, I think that you keep exactly the same property here for arrows to be lifted to Cartesian arrows. So you ask for that in a fibration. You ask for more, but I don't really care about that now. So you still ask for that, but you modify the definition of what it means for a Cartesian, for an arrow to be Cartesian. And you say that an arrow is Cartesian if this function here, or this arrow here, which was a function between sets in dimension 1, becomes an equivalence of categories in dimension 2. So you remember how I said that when doing higher category theory, you're always looking for statements that can be generalized like that, because hey, then you just write a line and you have a new definition, and that's always good, I guess. So here you just replace function bisection between sets by equivalence of categories, where everything is properly adapted, and you get a definition of a Cartesian arrow. Okay, and I want to look. So this can be a tiny bit involved. So we'll see how much time we have. But let's just say for now that you remember how we wrote that the arrow was a bisection and we separated it, we split it in surjective and injective. So now we have H essentially surjective, and this means that there are liftings, but the liftings here, because we are asking for it to be essentially surjective, we'll have two cells here and even one more, but let's just think that they have two cells like that, okay? And that's essentially surjective. And then you have full and you have faithful, okay? So when you write full, then you see that it means that if you have two arrows here, so two arrows in this category, and sorry, two objects here, so two arrows in the bicategory, which are objects here in this category, and two double cells, or two cells, sorry, in the bicategory, which are arrows here in the red. Okay, so given all of these, B, W, alpha, and beta, satisfying this equation, which is just the equation coming from the pullback here. Okay, so I'm not really explaining this with all detail, but you may believe this if you feel like it, or do the computations. So given B, W, alpha, and beta satisfying this, then there is a unique, sorry, here. So there's a unique, no, I shouldn't say unique, sorry. So I'm just doing full. So there is one, not necessarily unique. There is one beta hat, which will be mapped to this alpha and beta. So this means that P of beta hat is beta and F of beta hat is alpha. So it's kind of really the same situation that we have for the old Cartesian one, except that that now you write it for including the two cells, okay? But note that the two cells here are not necessarily invertible, okay? They're just two cells because we are writing full, okay? Great. And then you have faithful, which is maybe even more similar to what we knew before, because it says that for two parallel two cells, if they are equal after composing with F and they are equal after applying P, then they are equal. Okay, so you kind of recover the same properties that you had before, but with one dimension higher. Okay, so it's always a good way to understand the two-dimensional notions as generalizations of the one-dimensional ones, and that you can actually make very neatly the parallel between the notions. All right, so finally, and rather quickly, let's review the theory of bicategories of fractions. So bicategories of fractions allow you to localize bicategories instead of categories. So you still have a pair C, W. Now C is a bicategory, and W is still a subset of arrows. And you can compute the localization in a bicategorical way. So this means that the universal property here will really hold up to equivalence of categories, but we don't really care too much about this now. So I just want to mention that as Dorette did many years ago, you can put some natural conditions here, and you have your frag 2 and your frag 3. So these are kind of new names. These are not the original names. Same happens for frag 1. Okay. So this is the way this is done here in the 96, and also in a more recent paper by Dorette and Laura Szyld. Sorry. And so you can keep kind of the same fraction 2. You also can keep kind of the same axiom number 3. So you just replace equality by invertible, but then you have to add an extra condition. Okay, which is a bit long, so that's why I am not writing it here. Okay, and yeah, so I won't say anything else right now, but I will come back to this in a bit. So just remember that you can naturally modify axioms fraction 2 and fraction 3, but then you have to add some extra conditions in the axiom number 3. Okay, great. All right, so whatever time permits, let's kind of see how the proof would look in dimension 2. Okay, so that's kind of the idea. So what happens if you put here invertible 2 cells? Okay, so again, maybe I should say that fraction 1 is still no problem for us here. The Cartesian arrows still satisfy them. Okay, and maybe again, it's a good moment to go back to this strategy and remind you that we will kind of be using the same strategy. Okay, so the difference is now that this is a fibration of bicategories. Okay, great. So you put an invertible 2 cell here. So you start with an invertible 2 cell here. Sorry, no, let me start over. I'm ahead of myself. So this is the axiom. Given the red, then there is the blue satisfying that. So you don't start with any invertible 2 cell. You just start with this thing here in black. On top, you apply P, and you get, applying the axiom, you get here the invertible 2 cell. You still lift the Cartesian arrows like before, and you will have, by the property of Cartesian arrows, this one on top. So nothing changes here. Okay. The problem is here. Okay, and that's why I think that the first question that I got during the talk was a very smart one, smarter than what I did at first. That's for sure. Okay, so you wanna put invertible 2 cells here. Okay, and so you start here on top, just like before, and you start with an invertible 2 cell here. Let me see if I can zoom in a bit. So, okay, like that. So you start with an invertible 2 cell. You apply P, like you did before, and now what you have, which I didn't write before, is that you have PH, PS, and an invertible 2 cell, PH, PC. Okay? So if you just use the axiom for cofiltered, then you will get a 2 cell here. So let's call this one alpha. Let me see if it's a good idea to call it alpha or if I should call it beta. Let's call this one alpha, so that our notation matches the one that we had before. So here we have P of alpha, and here we will have beta, okay? But then we will have no relation at all between the beta that we had, the beta that we got, and the P of alpha that we had, okay? So here it becomes very clear that you don't really want to use this axiom, okay? You don't really want to use this axiom here. The axiom that you want to use is frac 3. Okay. Because if you use frac 3, then you get precisely what you need, okay? So that's really as much as I want to say, so as to not to go over time. But if you like, that's as much as I want to write. But if you look here at this condition, then this condition here is precisely what was missing here if you just use cofilter, okay? And it's exactly what you get if you use fractions 3, okay? So fractions 3 will give you a compatibility here, which is that P alpha, you can compose it, so P of alpha is here, you can pre-compose it with K, and you will get the same as beta post-composed with P of H. So if you use frac 3, then you get this, and then you get these new arrows and these new 2 cells satisfying exactly the compatibility condition in frac 3. So now is when I noticed that I forgot to say one tiny bit when I introduced frac 3, which is that not only you ask that if you have an alpha, then you have a beta, but you do ask for a compatibility there. And there, the coherence conditions that, the coherence requirements that Juan asked about, they play a role here, okay? So, hey, in a talk, you don't have coherence, all pseudo functors are 2 functors, and things behave nicely. But when you write them, you have coherence, you have pseudo functors and all of that. So here you have that alpha is here. So when you compose that with K hat, it's the same as if you compose beta with H, okay? So that's the third fractions axiom, okay? So this is the first thing you realize, that it's not the cofiltered axiom that you need, but it's the fractions axiom that you need. And then maybe it's a good idea to come back here and say, hey, maybe here the same happens. Maybe here, instead of thinking about pseudo cofilter, you can think of fractions too, because it really is the same axiom. It's just a circle instead of a C. And then you go here where I didn't go because I didn't have the time, but you say, instead of the cofiltered axiom, you can use, again, a fourth fractions axiom, okay? Which then we considered, okay? So what's this fourth fractions axiom? So this fourth fractions axiom, it's a new axiom. It's a result that was known to hold if you assume the fractions axiom, but it was never presented as an axiom. Okay, so the point that I want to make is that this makes of a nice fourth fractions axiom. Okay, and because it kind of follows the same pattern of 2, 3, and 4, that you equalize arrows, you given points, you get arrows, given arrows, you get 2 cells, and given 2 cells, you can make them equal. It's the same that happened with cofilter, okay? So you write this new fractions axiom, and then you get a proof of the result that vibrations lift fractions. Okay, so what does it mean, vibrations lift fractions? It means that you give a vibration, you assume that you have fractions in the bottom, and then you get fractions for a new family of arrows. What's that new family of arrows? Well, if you started with the family W here, then you get the Cartesian arrows which are over W. Okay, so that if you start with all the arrows, if you start with W, all the arrows, then you get precisely the Cartesian arrows, just like before. Okay, so you recover the pseudo-cofilter result because you can easily show, even more easily if you use the new axioms, you can easily show that if B is pseudo-cofilter, then the family of all arrows satisfies fractions, and then you have fractions for the Cartesian arrows. All right, so because I knew this would take quite a bit, I just want to read to you with the energy that I have left some takeaways that I wrote earlier. Okay, so showing a result that's linking different two-dimensional notions, that's what really allowed us to find cleaner versions of the axioms involved. And we found out that the real result, in a sense, was just for vibrations and fractions. So cofiltered colimits is really the example and the application that we have, and even though we are working in new applications. But it's not just that you have an example, it's just that if you do it like that, then you can't really generalize it to dimension 2. That's where you have an obstacle there. Okay, and then just say as an application that I won't go into unless you want me to in a different talk, that this new result really fits nicely with how you compute the pseudo limits of bicategories. So it's really a tool for computing a lot of colimits, and the proof that you have to use to do that, it's really the same as the one in SGA, and you use vibrations. So you get clean proofs of results which are very long to prove otherwise. Okay, so let's just stop there at the takeaways, and let me thank you very much for your attention.
Thank you very much, Martin, for the lovely talk.
Hey, thank you very much.
Well, are there any questions or comments for Martin?
Don't forget about Michael's.
So I have a question.
Yes.
Can I go? Yes. So two filtered means every finite diagram has a pseudocone, but
yes.
often, most of the time in two category theory, by finite diagrams, we also include cotensors by 2. Like, so
yes.
you would get let's say comma objects.
Yes.
So this sort of gives you a cell somehow. Okay. So did you have any use for that, or is that something that you've looked at?
This is something that surprised me, and I'm still having a hard time believing it, but this is the result that Pablo got, which is that if you ask for any finite diagram to have a cone, then any finite weighted diagram has a cone as well.
Any finite what?
Weighted.
Weighted, yes.
Yeah, so in particular, you get the tensors by 2.
Oh, okay.
Yeah, and that's surprising. I mean, but
it's very surprising.
Yeah, but that's really only true because you're just asking for cones and not for limits. Okay, so of course, it's not the same to ask for finite conical limits than to ask for finite weighted limits.
No.
Okay? But if you are just asking for cones, then surprisingly, it looks like it's the same to ask for finite conical diagrams to have a cone than to ask for any kind of finite weighted diagrams to have a cone. Okay, when you define cone, just like you use when you define limit. Okay, so that's why we really didn't have to go down that road, because it's kind of already included in the axioms. But personally, I find this to be kind of a bit pathological. Okay, and because it is only true for cones and not for limits. And at the same time, we don't really need to use the cones for the commas. Okay, so I'm still wrapping my head around it, but I can tell you what I know, which is that that surprisingly you get more than what you ask for, but you don't really end up using it. So we don't really end up using cones for tensors, sorry, or for commas or anything like that. You only end up using these three of the axioms.
Okay.
So thanks for the question. It's a natural question to ask, and we encountered that.
Thank you very much, Bob. Yeah, Carlos, go ahead, please.
Thank you very much, Martin, for this nice talk.
Thank you, Hans.
My question is maybe it's quite parallel. I saw this process of how to construct the category of fractions for suppose a small category, and there is this process of left calculus of fraction from Gabriel and Sisman.
Yes.
And I would like to know if there is a process for bicategories of two categories, and I also want to ask, for example, if you construct, suppose the category of fractions of a monoidal category or bicategory of two categories, we know by equivalent that the groupoid of, when you localize all the morphisms, you get the fundamental groupoid of the classifying space. So what you get more when you obtain the category of fractions of a category? Yeah.
Okay. Yes, that's a very interesting question. So I think I have two different things to say. So the first, maybe this is probably something that wasn't clear during the talk, so maybe I should emphasize that more. So yes, here I mean precisely to the conditions. These are frac 1, 2, and 3 are exactly the conditions that you can find in Gabriel-Sisman. So that's precisely the conditions that you have there for left or right, depending on which way you go, calculus of fractions. I know I always mix my right and my left, so let's just say one of them, calculus of fractions. And then the original article is the one by Doret from the 96, which is something like Etendues and stacks as bicategories of fractions and something like that. And back then, in that paper, she already gives the construction of the localization of a bicategory at a family of arrows, satisfying these fractions conditions. So you have that the conditions in Gabriel-Sisman can be adapted to bicategories, and you can say that that's precisely one of the things that Doret does in her 96 paper. So she gives this second axiom, and she gives this third axiom, in which you ask here for invertible two cells. And as you may have noticed, I forgot to add this compatibility, which is, again, I'll write that alpha k is the same as beta h. Okay, so this is condition frac 3, and she adds a furthermore to this condition, adding a further condition to frac 3. And what we are doing here is replacing this furthermore by a frac 4, sorry. So we are just giving axioms for a bicategory of fractions, which are equivalent to the ones that she had already given way back, okay? But at the same time, she already performed the localization. So she already constructed the localization back here, okay? So you can say that what we are doing here by changing this axiom is making them fit into this pattern, into the pattern of the SGA, because that's an important application of localization, to compute colimits by localizing the top bicategory of a fibration at the Cartesian arrows, okay? So kind of to sum up my answer, or my first part of the answer, sorry. So you have bicategories of fractions, and the axioms go way back to 96, and we are sort of giving a cleaner version, or a version of the axioms that fits the other two notions in a more clear way. You have the same kind of pattern that you had for fibrations and for cofilter, okay? But the construction of the localization is already here, So here, a construction is already made of a bicategory, which is the localization of C, a bicategory, and a family of arrows. And it's a localization in a bicategorical sense. So that's as for the part on the relation with Gabriel-Sisman. As for the relation with Quillen and the localization in that context of models, so in general, you won't have these fractions conditions, unless I'm mistaken, in that context. Okay, so I may be wrong, but that's my experience so far, which is not long, but what I seem to get is that if you wanna compute a localization, maybe you're thinking a different thing than I am, but if you want to compute a localization like a homotopy category of a model and things like that, which have a more topological, geometrical flavor coming from that area, then you will not have these conditions. And it's already so in dimension 1. So Quillen makes the point that this is a new example of a localization which doesn't satisfy Gabriel-Sisman. Okay, so I don't wanna push my work here, but let me just say that we've been working with localizations in that situation too, and you can do that, but it's a completely different scenario. So maybe let me ask you, Carlos, if were you asking because you were thinking of a link between fractions and localization in that situation, or just because it's localization?
No, it's I was working with the fundamental group of coordinates category, but a coordinate category is a monoidal category. So usually you just for finding the fundamental group, you just find, or you calculate the category of fractions, and so I would like to know if you calculate the category of fraction of the monoidal category, maybe you can get more structure. So that's what my point.
Yes. Fractions for monoidal categories, that's a completely separate issue. Yes, that may be a way to go. Yeah.
But also I would like to know, for example, when you have this the category of fraction of two category, you also the morphisms in the category of fraction are roots, no?
Yes.
In the diagram that should satisfy the localization will be the diagrams, but up to two morphisms, no? Yeah.
Yes. So one of the reasons why localization by fractions in a bicategory is way more involved is because you can't just keep the roofs as your arrows. You have to also save this information. So if you do a roof, then your roof is coming from an application of the fractions, right? Because you have, say, a left fraction. Like I said, I always mix my left and my right, so forgive me. So you have one of those, say, left here, which is this one here, and your axiom tells you precisely that then you get a roof like that, okay? So just in dimension 1. And in a sense, you may say that the reason why the arrows in the localization are given by roofs is because roofs are enough precisely because of the axiom, okay? So now think in dimension 2. In dimension 2, where the square here was commutative, now you have a 2-cell here, okay? And you cannot make reference to the 2-cell unless you keep all the information.
Oh, okay.
You see? So whereas in dimension 1, you could just keep the roofs to form your arrows, your length truth spans. If you do that for bicategories, you have to keep all the information of the square. Okay. So the computations become more involved in that case.
Okay. No, yes. Thank you, Martin. I understand.
Hey, no worries. Happy to answer.
Yeah, thank you very much, Carlos. Are there any other questions or comments? Well, if not, let's thank Martin for his great talk. So, thank you very much, Martin.
Okay. Thank you a lot.
Thank you, Martin.
It was nice being here.
Yeah, it's really nice having you. Yeah, and the talk was pretty great. I do like the format of the blackboard, the big blackboard, and moving around. It looks pretty cool.
Thanks. I found when I was preparing the talk that the slides really didn't reflect the way I thought of the situation. Like I used the expression like a mind map. So I tried to write it. I wrote it first in a sheet of paper, of course. Kind of wrote what was in my mind.